My name is Teng Zhang, and I'm from Nanjing University of Aeronautics and Astronautics. My topic today is the evaluation of droplet evaporation models for the LES of a turbulent dilute spray flame. And this work is supervised by Dr. Jinghua Li. This figure shows the complex processes involved in the spray combustion for the liquid fueled combustors. As we can see, the spray film injected from the atomizer into the combustor, and the spray breaks up into small droplets in the downstream because of the turbulence and because of the interaction of turbulence and spray. The small droplets evaporate into fuel vapor in these hot gases. So the spray atomization and evaporation plays an important role in the spray combustion, and which because they direct influence the combustion efficiency and combustion performance. So here we only focus on the evaporation and combustion. So these processes need accurate mathematical models to do the simulation. For the combustion, we use the tabulated chemistry model. Firstly, the flame master is used to calculate the 1D counter diffusion flame to generate the laminar flame light library for FPV or FGM. And then an in-house fortune code, FM2 delta, is used to do the PDF integration to generate the turbulent flame light model, flame light table. And then in the main simulation, these thermal variables can be retrieved from the turbulent flame light table by using these flame light controlling variables. These three equations are the governing equations in LES for the three controlling variables: the mixture fraction, the mixture fraction variance, and the unnormalized progress variable. For the unnormalized progress variable, we use the linear combination of the four important product species. The spray is solved under the Lagrangian framework under these assumptions. So the spray droplets are in dilute phase, and the droplet are spherical, and its diameter is far less than the LES filter size. And only the Stokes drag force is considered, and the infinite heat conductivity is assumed inside the droplet. So we can derive the droplet equations, the motion equation, the momentum equation, and the heat transfer and mass transfer equation. In here, the F1 is the correction of the Stokes drag force, and the tau P is the droplet relaxation time, and the Nu is the Nusselt number for heat transfer, and the SH is the Sherwood number for mass transfer. So basically, the droplet evaporation only involve these two equations. The F2 is the correction to the heat transfer due to the existence of the Stephen flow, and Bm is the Spalding mass transfer number. So this figure shows the schematic of a droplet evaporation. So imagine the droplet is surrounded by hot gases, by hot gas. The energy is transferred from the surrounding gas to the droplet surface, and the droplet is heated, and the fuel vapor is evaporated from the surface to the surrounding gas, and then the gas vapor film is formed between them. So this plot shows the boundary conditions of the droplet equations. So here comes the question: how to calculate the mass fraction of the fuel vapor at the droplet surface, the Ys. One simple way is to assume the droplet surface is in the equilibrium or the saturated state. So the surface vapors molar fraction can be calculated using the Ross law, and then the saturated pressure can be calculated using the Clausius-Clapeyron equation, and then the mass fraction of the vapor can be derived using this formula. However, usually the droplet surface is not in the saturated state, so the non-equilibrium effect should be considered. So in the Langmuir-Knudsen model, a correction term is introduced to the molar fraction, to the surface molar fraction, and the LK is the Knudsen layer thickness, and the beta is a non-dimensional evaporation parameter. Then the supporting mass transfer number can be calculated using the non-equilibrium mass fraction. Here we can see in the formula of beta there is a dot MP in it. So that means if we want to solve the mass transfer equation in the Langmuir-Knudsen model, it needs an iterative procedure to solve this to get a converged solution. So in our simulation, about 5 to 10 iterations is needed for each droplet. Another question is the correction of solution flow. We can see the mass flux and the heat flux is opposite. So that means we should correct the heat transfer because of they are in the opposite direction. So one popular solution is to use the burst correction. The F2 term, the correction factor F2 in the heat transfer equation can be written in this formula. We select the CRSB spray flame as the target case. It's an open burner using the inhabitant as fuel, and there are 18 straight winds to generate the highly turbulent but non-supporting air-cooled flow. A simple injector is the spray is injected to the atmosphere using a hollow cone injector. So from this picture, we can see the flame is lifted off from the injector. So this makes the simulation with result very sensitive to the models we selected. The guys at Korea, they conducted many experiments to get the gaseous and liquid phase results, and also the flame shape. This picture shows the computational domain and the slice of the mesh of our simulation. A cylinder in the length and diameter of 300 millimeters is chosen to represent the atmosphere environment, and the total mesh count is more than 6 million cells. The air and fuel mass flow rate is relatively small because this is a lab scale burner. The global equivalence ratio is 0.7. For the SGS model, we use VIEW with the default model constant. A detailed happening mechanism is used to generate the flamelite table. For the tablet chemistry method, we use the diffusion FGM method. And the final chemistry table contains 100 times 50 times 100 grid point for each of the controlling parameters. The cone nodal injection model is used to represent the hollow cone spray, and the Rosen-Ramler distribution is estimated using the first available experimental results. So in our present work, we studied 3 evaporation models. The first 2 models are used to study the effect of the burst correction, and the latter 2 models are used to study the effect of a non-equilibrium. These 3 large ideal simulations are conducted using our in-house solver as FM3 form. The TVD scheme is used for the momentum and other transported scalars. The time step is 1 microsecond to make sure the maximum quantum number is less than 1/4. Firstly, we conducted 8 flow-through attempts. 8 flow-through attempts to make sure the spray flame is fully developed, and then another 8 flow-through attempts was conducted to collect the mean flow field. So before we get into the spray flame, the single droplet evaporation problem was studied. The experimental data is taken from this reference, and the zero-dimensional simulation was conducted using the droplet evaporation code from this reference. The single droplet is inhabiting, and its initial diameter is quite a lot. It's 500 microns. So these two figures shows the diameter and the temperature, the evolution of the droplet diameter and the temperature. So from these plots, we can see the rapid mixing model without burst correction predicts extremely high evaporation rates. But when taking into account the Stephen flow by using the burst correction, the RMB and the LKB model has the same solution, has the same results. So then we studied the droplet evaporation for diameter from 10 microns to 75 microns in the flame-like condition. So from here we can see the temperature of a base gas is from 500 Kelvin to 1500 Kelvin. So we can see from the evolution with the diameter that only for the low temperature case with the decrease of the initial diameter, the RMB model and the LKB model have small differences. This shows the non-equilibrium effect only has the non-equilibrium only has a minor effect on the only have a minor effect for the small droplets at a lower temperature. So for the spray flame, these are the instantaneous axial velocity overlapped by the droplets. The 3 evaporation models have similar results. We can see from the distribution of the droplets that the small droplets, when traveling through the turbulent jet, the small droplets can be easily entrained by the turbulent flow, but the larger droplets can travel through the high-speed curve flow to the outer region of the jet. And these are the instantaneous temperature contours overlapped by the droplets. So we can see the flame is lifted off from the spray injector, and these small droplets are survived because of the low temperature. And but in this in the flame region and the hot region, the flame evaporated very fast. So for the flame topology, there are the contours of the instantaneous and the mean mass fraction of OH at the middle cut plane. We can see the CRSB flame can be divided into these 5 regions. The flame stabilization base, and S is the flame base, and A is the turbulent jet region in a very low temperature, and C is the hot region in a relatively high temperature. And IRZ is the inner reaction zone, which is highly wrinkled by the turbulent shear layer. And ORZ is the outer reaction zone, which is very stable and smooth. These three, the flame topology and the local extinction phenomena are well predicted by these three evaporation models. But however, the flame base, there are some difference in the flame base predictions. The RMB and the LKB model has a very similar result for the flame height and the flame and the radial locations of the flame base. But the rapid mixing model without the burst correction and predicts larger flame height and radial locations. These radial profiles are the gaseous axial velocity, mixture fraction, and temperature. The left column is the time average values, and the right column is the RMS values. So for the axial velocity, there are some difference between the RM model and the other two models. So the axial velocity was underestimated by the RM model. The difference between the models are more obvious in the mixed fraction and the temperature profiles. We can easily see from these results, the RMB and the LKB model has very similar results, but the RM model, the flame in the was radially was expanded in the radial direction by the RM model. So this is the liquid phase results: the droplet axial velocity, the droplet mean diameter, and the droplet temperature. The axial velocity and the mean diameter was a little higher in the simulation at the first station, and the difference between the models mainly exists in the radius larger than 10 millimeters. For the diameter and temperature profiles, the RM model predicts lower droplet temperature and higher diameter in this region because it has the lowest gas temperature in these regions. All right. So to summarize, we conducted the large edge simulation of a turbulent dilute spree flame, and the effect of the burst correction and non-equilibrium on the droplet evaporation are investigated. So the results shows that the models with the burst correction have similar results and agree better with the experimental measurements. So due to the existence of Stephen law, it's important and necessary to adopt the burst correction when simulating the spree flame. But for the non-equilibrium effect, it only has very minor influence on the global flame structures. For the future work, we are working on the implementation of more advanced evaporation models.
Okay,
all right, thank you.